Well, this is work with my co-authors Danny Groenewegen and Ilko Visser, who is sitting over there. So thank you, Emina, for introducing DSLs, because this is a DSL. The name of the DSL is IceDust, and the title reads Incremental and Eventual Calculation of Derived Values in Object Graphs. It's a kind of a complicated title, so let's look at this title. So we're talking about object graphs, which are a data structure. We want to have this data structure persisted, and from this data structure we calculate derived values. So we process data and we find out new data. And the way that we can calculate this new data, we can do this in an on-demand fashion. So when we write to base data, we do nothing, we just save it. And when we ask for the derived data, we will calculate it at that moment. Or we can do it incrementally, and that means that on a write of base data, we will compute all the derived data, and then when we ask for the derived data, we can just directly return the cached value. Or we can do eventual calculation, which means that we schedule updates, so we might possibly read outdated values, but the writes and the reads will both be very fast. But let's first look at a domain, the domain of information systems. So what's an information system? An information system is a system that stores and organizes data. And here you see a screenshot of an information system for course management. And if we zoom in, then we can see that this information system stores the structure of a course, and we see lectures and lab and exam. And if we look at a specific lab, then we see the individual labs. And if we look at a specific lab, then we see individual assignments. So these are structured as a tree. Courses are structured as a tree in this system. But not only does the system store and organize data, it also computes derived data. And for example, here we can see the started percentages, the completed and the past percentage of students, and the average grade. And this is calculated from the individual student grade. So this is what we call derived data. If we look at this more abstractly, we can represent this data as an object graph. So here we represent a course as a tree. It consists of a lab and an exam, and the lab consists of two separate labs, and this tree can of course be as complicated as you want. In the system, students are also objects, and students submit answers to these assignments. So here you see that Bob has 3 submissions, and for the answers he submits, he will get grades. Now in this specific system, we also have submissions for the collection assignments, which we call collection submissions, and that's because these submissions themselves are a tree. So this is how we represent object graphs, and derived data we represent as these attributes with ... because these needs to be computed. Well, if you want to compute these things, for example, whether Bob actually passed the course or what kind of grade that he got for the course, we need calculation rules. So the first rule that we specify is somebody passes if his grade is higher than the minimum grade. Well, that's of course kind of logical for a university. And for the collection submissions, we say, well, the grade is actually the average of the child grades. So the grade of the lab will be the average of the individual labs, but only if all the children pass, because we don't want a student to fail a single lab, but then succeed the complete lab and succeed the course. And if we apply these rules, we can see that Bob unfortunately fails this course because he failed the second lab. And that's why he didn't get a grade for the full lab, and he fails the full course. And of course, we can make these derived values more complicated by stacking them on top of each other, so we can, with the student grades, calculate the average grade for the course. So if we have such kind of object graphs and derived values, these are kind of easy to implement if you use an object relational mapper for persistence, and if you use getters to specify these derived values. But if you use getters to specify derived values, that also means that you will use on-demand calculation. And this is kind of nice, but if you have a very big course with 10 labs and every lab 10 assignments and then 250 students submitting answers, that means that the average grade of the course will now depend on 25,000 values. And if you use an object relational mapper, that means that every time that you get a request to display the average grade, you will load 25,000 objects from the database and calculate every time you ask for this. So this is not efficient. So rather than on-demand calculation, in this situation, we want to use caching with incremental cache maintenance, so that on reads of average grade, we will get a very fast result. So how does this work? If we have such an object graph with all the cached values, and if we change Bob's grade for the second lab, then now we have an inconsistency. The data is not consistent with the rules anymore. So we need to update all the data, the derived data that depends on the original data. So if we change grade, we need to update pass. And if we change pass, we need to update the parent grade. And this cascades all the way to the top, where we need to update that Bob did now actually pass the course and the average grade of the course of all the students changed. Problem is that if you write this code in Java, it becomes much more complicated. So on the left-hand side, we have the original getter, which is fairly trivial. And on the right-hand side, you have to reason about cache and about cache maintenance. And this is just for one single getter. But of course, your actual logic will be much more complicated. So you'd rather not write this. But there's another problem with this solution. And that's in an information system, it's often the case that you get concurrent changes, because there's many people interacting with the information system. And if you get concurrent changes of base data, then the aggregated data can conflict. So if you have two concurrent threads trying to change the grades of Bob or of different students, then if they eagerly try to maintain the cache, they will both try to change the aggregated values. And this will result in conflicts. So rather than only using incremental calculation, you would want to use eventual calculation in such a situation. And in this way, you can schedule the updates on a different thread and they won't conflict, but you will get outdated values. Of course, the Java code for this is even worse. So if handwriting the caching code and eventual code is painful, why would you handwrite it all? Can't we just, transform Java code automatically? Well, for the simple example, we could, because I just did it on the slides, but in general, you have to deal with aliases. We just had a very nice talk, and mutation and many other features that make this problem really hard. So can't we use functional reactive programming? I mean, they do this propagation of change. Not really, because functional reactive programming needs all the data in memory, and also because we use an object relational mapper and have concurrent requests, we actually load parts of the data in memory, and we can load the same data in memory twice. So this is not a nice fit. Or if I have a database, why don't we use materialized views? Well, materialized views don't allow recursive aggregation, and we need recursive aggregation for our example. So if we simplify the world to a very small table, which is oversimplification, you can see that with all the solutions, we have a problem. So, of course, that's the motivation of IceDust. So what does IceDust do? Well, in IceDust, we specify object graphs in a DSL, in a domain-specific language, and we specify derived values in a domain-specific language. And then the IceDust runtime will persist this data and calculate either the derived values on demand, incrementally, or eventually. So what does such a specification look like? So here we come to some DSL code. At the top right, I will show the object graph that corresponds to the definition. So in IceDust, objects, the types of objects are governed by entities. So here we specify, well, we have submissions and assignments. And these entities have attributes. So here we specify, well, submission has a pass, boolean, and an optional grade. And the question mark indicates that it's optional. Now, all attributes in IceDust can only be of primitive types. You cannot have an attribute of a type of another entity, because actually all the entities are related through bidirectional relations. So here we specify the parent-child tree of assignments. And these red question mark and star indicate how many of these relations there are, or that there can be. So we have at most one parent, but we might not have a parent, and we have 0 or more children. And we can continue this and say, well, submissions are a tree as well, and we have an association between assignments and submissions. So that's how we specify a data structure, the data model in IceDust. Now, on this data model, we specify derived values. So we do this in this fashion, where we say, well, we pass if the grade is higher than the minimum grade, and otherwise false. And we need this otherwise false because we might not have a grade. And if we don't have a grade, we cannot compare it to the minimum grade. And we can continue this and say, well, the grade is the average grade of the children, but only if all children pass. And if one of the children doesn't pass, we don't get a grade at all. And we can specify the average grade of an assignment in the same way. So the last thing that we need to do is specify that this is a default value. And default value means the IceDust runtime will calculate the value for you from this expression, but you can override it. So it's a default value, but you can override it as a user. And we use this to specify the grade of students in the leaves of the tree, but also if we want to override Bob's complete grade for the course, we can override it. So if we go back to the overview, we can see, well, we have an IceDust specification with object graphs and derived values, and the IceDust compiler will compile down to an object relational mapper and compile down to getters. But more interestingly, the compiler can also do the more complex calculation strategies. So how does it work? If we go back to our example and we see the propagation of changes, then actually the propagation is governed by paths. So if we change grade, we need to update paths, and if we change paths, we need to update parent's grade, and this cascades all the way to the top. So if we have such an IceDust specification which we just built, how do we get these paths? So let's look into a specific example. So if we look at paths, we can see that we define paths as the grade being higher than the minimum grade, and if there was no grade, then we don't pass. So actually, if we look at this expression, the only thing that matters is the grade, because all the others are just binary operators and literals, and these don't change, so we never have to update pass on the change of these. So actually, if grade changes, we need to update pass, so pass is dependent on grade. And if we go to the other examples, we can see, well, grade depends on the children pass and on the children grade, but it means that if we change children, we have to update grade as well. So all subpaths we also depend on. And we can do the same for average grade. Now, the next step is that we actually need this bidirectional relations. Because to go from dependencies to data flow, you need to invert the paths. And to invert the paths, you need to have a bidirectionality. So if we start to invert these paths, we can see, well, for the first one, we don't need a relation because it's just an attribute in the same object. So if pass depends on grade, and if we change grade, we need to update pass. But for the next one, we can see, well, if grade depends on the pass of children, that means that if we change pass, we now have to go to the parent and trigger an update for its grade. And the same for the grade. If we change a grade, we need to go to the parent and update its grade. And if we change children of an object, that means we also need to reevaluate grade. And if we change parent, which is the inverse of children, we need to update the parent grade. But I omitted that last one because it's actually part of the calculus, so you don't have to reason about it here. And we can do the same for the average grade. So if we change the grade of a submission, we need to update the average grade of the assignment. And if the submissions of an assignment change, we need to update as well. So if we take this and we sort them so it's easier to read, we can go back to our running example and see, well, if we change the grade of Bob second lab, then we can look up in the table, oh, we changed grade. So now we need to update pass, parent grade, and assignment average grade. Now, we don't have an assignment average grade here because, well, there's no connection here. So in general, these paths can evaluate to 0, 1, or more values. And every value that you find, you need to trigger to update. And of course, this cascades. So we now update pass, so that means that we also need to update parent grade, and this cascades. So in the end, we update everything. So this is how IceDust does the calculation strategies, and basically, for the incremental one, we do the calculation directly after the write on the same thread, and for the eventual one, we schedule the update on a different thread. So how does this perform in practice? Now, if we look at requests per second on the left axis, so higher is better, and on the bottom axis we see read-write ratio, which means left is only reads and right is only writes. We can see that the on-demand performs much better if there's only writes. And this is, of course, very logical because on a write we didn't have to do anything, we just saved the data. But reads are very expensive for on-demand because you actually have to load all this data from the database. And you can see that, well, it becomes very slow. This is a logarithmic scale, so we actually slow down considerably. On the other hand, if we do incremental calculation, we see the exact opposite graph because it's very cheap to read from the cache, but if we change data, we actually need to transitively update everything that depends on it. But because this is a very concurrent workload, very concurrent benchmark, we also have this dashed line here, which indicates the number of failures. And this is exactly because we are benchmarking with one single course with many students, which means that every concurrent change will propagate all the way up to a concurrent average value change of the course, which then conflicts on the database level and will cause transactions to fail because there's optimistic locking. So if we go eventual, we have great performance everywhere. But of course, we lost our strong consistency because now we don't actually know whether the grades are up to date. So if we compare this, you might say, well, we knew that on-demand was going to be slow on reads, and well, eventual was always fast, but this incremental where you get your consistency doesn't have any use at all because you have a lot of failures except for the case where you only do reads but you never write anything. And the crux here is that it does have a use, but not if everything concurrently aggregates into one single value. So if we change the benchmark and we look at a different number of trees that are completely separate, so you can think of this as different courses which have the same amount of students and the same amount of assignments and the same amount of workload, so students submitting new answers and getting new grades for all these different courses at the same time, then we can see that the on-demand calculation doesn't really care about this, but if we look at the incremental one, we can see that the more concurrent courses that we have, the less performance penalty we get. And if we go with 16 or more, then we can see that it actually is less than 1% failures, and well, 64 courses we had no failures in 15 minutes run at all. And of course, Eventual performs very steadily as we expected. So if we go look at the overview, we can see, well, for fast writes and simple derived values, and that's like up to 100 base values, we can use on-demand calculation. It's fast, there's not so much overhead, we load a couple of objects from the database. If we have more complicated derived values, but they are separated, and they have concurrent workloads, we can use the incremental calculation. But if you want to have fast calculation always, and you don't really care about that your values might be a couple of seconds out of date, then you can use eventual calculation. Now, it's very important that we can generate all of these from the same ISO specification because you might not know upfront which ones you need. And this brings us to one of the future work things, which are actually triggered by one of the things we didn't know upfront, is that if we have incremental behavior, then this is very good performance during homework. So during homework, students submit new answers, and we have an automated grading system for programming assignments, so they get new grades. And this is all very fine for homework. But during an exam, you have so many students that concurrently submit new answers that this is very bad performance because we have conflicts in the aggregated values. So maybe rather than doing everything incremental, you might want to compose these different strategies. And currently, IceDust just compiles the whole specification with one strategy. So in future work, we would like to compose these. But we cannot blindly compose these because we would compose them the other way around. We would actually not get any update triggers because getters don't trigger any events for updating changes. So we would like to have a type system that ensures that we only have sound composition. Also in future work, we would like to increase the expressiveness of IceDust. So for example, in this, where we have the assignment tree and the submission tree and Bob, then we actually have redundant data. And the redundant data is a submission tree, because if we do a pattern match on the object graph, we can actually figure out that there's a parent-child relation between the submissions. And this is exactly what, for example, Datalog will do for you, or MySQL, but IceDust doesn't do this because we only do derived attributes and not derived relations. So this brings me to the end of my talk. We started with object graphs, and we specified derived values over these object graphs, and these specifications we can write in the domain-specific language IceDust. And the IceDust runtime provides us with persistence, on-demand calculation, or incremental calculation, or eventual calculation. Thank you.
Looking at the language by which you were specifying relations and attributes and such, I couldn't help noticing a significant resemblance to previous things like alloy, for instance, even down to the word relation.
Mm-hmm.
I wonder if you could contrast what kinds of things you choose to express this way that are compared to how you would express it in Alloy, for example?
Yeah, so I think Alloy has a very similar syntax, but Alloy is much more powerful because it actually allows first order logic. And we were interested in incremental calculation of these values. So we have a very restricted expressiveness to allow for incremental calculation. So, but from the specification point of view, it's very similar to specify a model in Alloy or in IceDust.
Hello. I'm just wondering what happens when writes to the base values happen at a much higher rate than the calculations can propagate through the graph. So is eventual calculation the way to go there?
Yes.
Okay, thank you.
So have you considered implications of reformulating the approach such that you would work on streams and possibly skipping a lot of elements in the streams such that you don't perform intermediate calculations? Sort of turning the whole thing upside down, but it might still be useful to think about that.
Right, so if you do successive changes and you use eventual calculation, then you will actually skip the values that are not interesting anymore. So if you change Bob's grade 3 times and only then the eventual calculator will come by, then it will just process the one Boolean flag, oh, I need to update this, and it will read the latest value. So it will only do the changes once. But for the incremental one, it will, of course, because you want to have the consistency of the derived values, it will compute it 3 times, because it will only actually succeed if it changed the base value and all the derived values in a single database transaction.
Should we take the speaker again?